integrated rate equations is where we're heading to now, and this is where, for me, is probably one of the areas where I use kinetics probably the most. It is pretty nice stuff, and I think you'll kind of appreciate some of it as well, because it's here where you get to start thinking about stuff that you've experienced before in your life. So a rate law, as we know, expresses our rate as a function of reactant concentration. You can see that right here. Rate is equal to a proportionality constant that we call the rate law times concentration raised to some power. And in our case, we have focused on zero order, first order, and second order reactants. So when n is zero, we call that zero order, and so on and so forth. Now we're going to change the way that we kind of think about reaction kinetics. Instead of looking at what the rate is as a function of concentration, we're going to actually just study a single progress curve. And just to help you remember what a single progress curve is, okay, we can look at the loss of reactant as a function of time, or the gain of product as a function of time. And when we did that, we saw it might look like that, for instance. Doesn't always look like that. That's just an example. So it would be nice if, instead of doing a bunch of experiments where we have to measure a given rate at a bunch of different concentrations of A, what if we could get a lot of the same information from a single progress curve? Well, we can. And that's because we can use something called the integrated rate equations, or rate laws. I use them interchangeably. So you'll have to get used to that. Anyway, let me just move this out of the way here. With the integrated rate equations, or rate laws, we express reactant concentration, not rate, but reactant concentration or product concentration as a function of time. And mathematically, then, we can get information from that progress curve. And I'll describe that in greater detail as we move on. It comes from calculus. And if you remember, rate can be a derivative. Those who know calculus will know what I'm talking about. Those of you who don't, just ignore it. And since this is a derivative, it turns out we could take each rate law and integrate the rate law with respect to time. And that's what we're not going to do that in this class, but we're going to look at the products of doing so. That's what we call the integrated rate laws, or integrated rate equations. They give us a really nice way to study reaction kinetics. We can get information about the rate law from a single curve. So I can actually, by playing around with this, I can actually get the rate law, this rate law, from a single curve. Instead of measuring a bunch of different rates at different concentrations, I could do it in one shot. So that's one useful thing. We can also predict how long it will take to reach certain reactant or product concentrations. And that's nice if you're trying to predict something. Like, for instance, let's say you're a drinker and you drink some alcohol, and you want to know how long will it take for that alcohol to reach the maximum blood alcohol level. And that's when you'll probably feel it the most. But more importantly, let's say you plan to drive later on after that drink. Well, you can actually, there's a way to determine how long it takes for that alcohol to leave your body. And actually, toward the end of this set of notes, we're going to do some calculations on just that thing. So there's something else called pharmacokinetics. It also thinks about, like, how long does a drug last in your body? Like, let's say you take some aspirin. How do they figure out the dosages and how often you need to take them? Well, that comes from kinetics, this stuff that we're going to cover. And that's stuff you can actually calculate from the integrated rate laws. And then another thing, you've probably heard of C14 dating or potassium argon dating. These are radiometric methods of dating. They deal with radioactive decay. Well, we can actually use integrated rate laws to date things. So carbon dating, all that kind of stuff, that's an application of the integrated rate laws. And so that's one of the reasons you'll see later on that I actually start covering radioactivity as part of this section. Well, let's dive into the first scenario. First thing I'm going to talk about is the zero order integrated rate law. As a reminder, here's what the rate law looks like for zero order. But if we were to integrate it with respect to time, we would get this relationship that we would get. I'm going to actually make one little small change here. A sub t, I'm going to put A sub t here, and I'm going to call this initial. Okay. This will be A sub t, that's the concentration of reactant at any given time t, is equal to minus k, k is your rate constant, times time, plus whatever your initial concentration of reactant was, your starting concentration. That's what A naught means. That's why I changed this to A naught. Okay? And this actually, if you were to plot A sub t as a function of time, like you see down here, and it's zero order, it's going to be a straight line. Okay? Where the slope of that line is equal to minus k. So let's look at that. So y equals m. So the k then is your slope, and then t is x. I need to clean this up. Sorry about that. T is x. And then your y-intercept, or your initial concentration, is b, is your y-intercept. And so you'll get a straight line if you plot A sub t versus time if you have a zero order relationship. Okay? Let's move on to the next one. First order. First order is a little more complicated. There's more options for you in terms of the types of equations you can use. And so if we look at the integrated rate law for the first order reaction, just a reminder, rate is equal to k times concentration to the first power. We can also write it k times the concentration. And we can express it in a bunch of different ways. Straight out of the calculus comes this particular relationship. And again, I realized that t got left out here, so we'll put that there. So A sub t is equal to A sub 0 times, that's e as in the exponential function, minus kt. So if we want to undo that, the exponential, well, then we take, that's where natural log comes in. So another way to write this, and this probably for me is the one that I use the most, this version of it. If you flip, essentially you just flip these two things around, you get that, and then it drops the negative sign. That's another way. Honestly, I can think of times where that would be useful to use, but it's certainly not required. And then there's kind of the linear method. This is sort of breaking it out so it has the shape of a line. So if I were to look at these, I probably use this one the most, this one second most. And so just like we did, if we can use this, and I know you're going to use this in your lab, you take the natural log of your reactant, plot it against time. Okay? I'm going to make the same fixes here. I don't know why that got left off. And this is 0, that's A sub t. So if we take the natural log of A sub t versus time, and it's first order, we're going to get a straight line where k is your slope, t is your time that you do, and then your y-intercept is the natural log of A sub 0. So it looks a lot like the order, except now we got some natural logs in there. And so these relationships I'm going to show you about in a little bit, how we use this. You'll be using in the lab, you'll be using the plotting method to figure out, you know, what your order is and stuff like that. Okay, so let's move on. Second order. So here's the second order integrated rate law. And again, just in a very similar way, rate is equal to K times your concentration of the second power. That's your rate law. If you integrate it with respect to time, you get 1 over A sub T. 1 over A sub T is equal to KT plus 1 over A sub 0. And so here, K is your slope, and 1 over A sub 0 is your y-intercept. So you have, if you have a second order process and you plot 1 over the reactant concentration that remains at any given time t versus time, you'll get a straight line if it's if it's second order. So let's move on. Now I want you to see this. When you're trying to determine the order, you do all three plots, the A versus time plot, the natural log of A versus time plot, and the 1 over A versus time plot. The one that gives you the straight line, if in this case, when this is zero order reaction, the only straight line you're going to get is when you plot A sub T versus time. If you plot the natural log of A versus time, or 1 over A versus time, you're not going to get a straight line. So you'll know what the order is purely by which one gives you the straight line. So this one gives you the straight line, so we would know, and for this reaction, we would know that if I were to write this out from this, I could say, okay, I know that A is going to be zero order. I can get the value of K from the slope of that line, so I can get that automatically. I see what I did here. I gotta change it to the 0 power. There's rate. I know it's not that one and that one because they're not straight lines. So it's got to be 0 order in this case. And if we look at it, we can simplify it. We can say that rate is equal to K because concentration of reactant doesn't matter. So I can figure out a rate law simply by determining which one has the straight line. Let's say I was looking at a reaction where my reactant gave me a straight line only when I plotted natural log of A versus time. That gives me the straight line. That's the first order plot. It gives me the straight line. So that means A is first order. So if I were to go ahead and write rate is equal to K, and K is going to come from minus slope here, times A. And that's first order. Notice those two are not straight lines. So you know that they can't be. So for the same data set, you plot it 3 different ways, and the one that gives you a straight line will tell you what the order is. And then from a linear fit, so you can use Excel or something like that, and get a fit to the line, and you can figure out exactly what K is as well. And then finally, for a second order reaction, if you try to plot A versus T, or natural log of A versus T, you're not going to get a straight line. No straight line. So you know that neither of those can be the case, but in the case of the second order reaction, 1 over A versus time, well, you'll get a straight line, and the slope gives you K. So I can say, okay, I can write down what my rate law is because I know it's second order because I got the straight line when I did this plot. That's equal to K. Where do I get the value of K from? Here. And that's times A to the second power. So that's what I get when I do that calculation. Okay, let's do a little quick and dirty problem here. So let's say I have 3 plots. Oops, didn't mean to do that. Let's say I have 3 plots. I have one data set and I plotted it 3 different ways. I plotted concentration of A sub t versus time, natural log of A sub t versus time, and then 1 over the concentration of A sub t versus time. And just for fun, let's say our time's in seconds. And our concentrations have units of molarity, okay? All right. So we got these 3 scenarios. Okay. Okay, those are my curves that I get. Okay? And I had one straight line, and let's say my straight line was something like this. We fit this line, and I got let's say that's what I got when I did this fit to a line. Okay? What is the rate law? And put the correct units on K. So you got to include K and then have the right units for it. All right. So if you look at this, we took a data set, we plotted it 3 different ways. 3 different ways, same data. And so by doing these plots, all 3 of them, we find that only one gave us a straight line, which is what will happen. Only one will give you a straight line. Now, maybe if your data sucks, you might get some poor fits that look like a couple could be straight lines. In those cases, you have to use statistics and figure out which one is truly the straight line. But in practice, that's usually not a problem. You might see something like that when you guys do this for your lab. You will be doing this for your lab. You're going to collect some data. You're going to plot it 3 different ways. And whichever one gives you the straight line, that's the one that tells you what the order is. Okay, what's the rate law for this? Well, okay, I know that it's rate is equal to K times A to the first power. I know that because this is a first order plot. Natural log of A sub t versus time is a first order plot. A sub t versus time, this one here, whoops, A sub t versus time is a 0 order plot, and 1 over A sub t versus time is a second order plot. So the first order plot is the only one that gave it. So I know that this is first order. And I know then that if we remember, K is equal to minus the slope. So minus 18, so K is going to be 18. And rise over run, do you remember that? Rise over run is what a slope means. And so rise over run, well, when you take the natural log of a unit, the unit disappears. So in this case, all we have is time units. And it's over time. So it's going to be to the minus 1 times A. So that would be the rate law for this. That's how I can do this from one experiment. I plot it 3 different ways, and the one that gives me the straight line is the one I can get the information from. All right, half-life. This is the last thing I want to cover in terms of content for this video before we start getting into some practice problems and working out some practice problems. So there's this thing called the half-life, and it turns out it's pretty handy. We can use it for a lot of purposes, and I want to kind of give you first the definition of half-life. That is the time it takes to the time it takes to cut the initial reactant concentration in half. So it's the time it takes to cut the initial concentration in half. And in doing that in real time, I kind of stink at typing. I think I just come to that conclusion. Anyway, so it's the time it takes to cut the initial concentration in half. So another way I could state that is that the half-life, which I will call T1 half, is the time it takes for the concentration of A0 to reach 1/2 A0. Now, for a variety of reasons, it turns out this really is only useful in a first order reaction. And so I'm going to focus our use of half-life, T1 half, for first order reactions. So I'm going to show you how to derive the half-life. So we start off with the first order reaction, A sub T, or equation I should say, divided by A0 is equal to minus KT. That's one of the equations that we covered. Now, what I can say is let T equals T1 half, so let time equal the half-life when A sub T equals 1/2 A sub 0. So now I can go and substitute in those terms, and I can make something very specific for half-life. So I can say, okay, let's substitute them in. So natural log, and in place of A sub T, I'm going to put 1/2 concentration of A sub 0 over A sub 0 minus K T1 half, because this is that special case. And here's why first order is useful, because I can cross those out, and therefore the half-life does not depend on the initial concentration. In other words, it's constant for the entire reaction the whole time. For zero order and second order, that is not true. The half-life changes. The half-life changes depending on what your starting concentration of reactant is. Okay? So I'm just going to keep going with this derivation. Okay? I'll move these things up a little bit now. So to keep going, then I've got the natural log of 1 over 2 is equal to minus K times T1 half. And if I take the natural log of 1/2, that gives me negative 0.693 is equal to minus K. Remember, K is the rate constant times T1 half. And if I go ahead and divide both sides by minus K, I get the following equation. And this is a very handy equation, and it only works for first order reactions. T1 half is equal to 0.693 divided by K. So if you know the T1 half for a first order reaction, the half-life, you can calculate K. And if you know K, you can calculate T1 half. For zero order and second order, you won't be able to do this. And that's kind of the thing. It's the for those, half-life is not as useful. In fact, I've never used the half-life expressions for zero order or second order because they really don't give me any information, because everything depends on what your starting concentration is. And so in other words, the half-life is not constant. But half-life is constant. In other words, it doesn't change. At a given temperature anyway, it doesn't change. So half-life is constant for first order reactions. And that's pretty useful. All right. Now we're going to do some practice problems. All right, now it's time for some practice. We're going to do a few problems so you can kind of see, maybe get some feel for how some of this integrated rate law stuff can be useful. We'll start off with maybe some things you haven't thought much about, but then I'll bring it into your realm in the next. After this set of examples, I have another one that I think you'll get the connection to how kinetics can be useful, especially when you start bringing in the integrated rate laws. Okay, so in this first case, it says the rate constant for a first order decomposition of cyclobutane, C4H8 at 500 degrees Celsius is 9.2 times 10 to the minus third reciprocal seconds. So that's the first order rate constant. How long will it take for 80% of the sample of cyclobutane to decompose? Well, this is exactly what the integrated rate laws are great at. Okay, so since this is first order, you have lots of different choices, forms to work with. The one that I think will work best for this one is this. So I'm going to write it out. So natural log of A sub t divided by A0 is equal to minus kt. And what we want, we know that we want 80% of our sample to decompose. So that means that you want, so 80% decomposes, you want to think in terms of what's left. Okay? If 80% of A decomposed, if 80% of that's gone, then 20% remains. So what we want to do is find out where the ratio of A sub t over A0, remember A0 is our initial concentration, and A sub t then is the amount that remains after. And we want that to be equal to 0.2. Okay? I'll write it this way because there's 3 sig figs there. So we'll take natural log 0.2 is equal to minus, and then our value for k is 9.2 times 10 to the negative third reciprocal seconds times time. And time is what we're solving for. So then we can simply plug that all in and get what time is equal to. So if you divide both sides by minus 9.2 after taking the natural log of 0.2, then time is going to be 175 seconds, because we have reciprocal seconds right there. So when you do the math, that's how long it will take to decompose 80% of your sample. So you only have 20% left. So it's part of the challenge of these problems is kind of making sense of, why did I pick 20% when they say 80% here? And that's where you have to pay attention. If they said something like, how long will it take for 80% of the sample to remain, then I would have put 0.8 there. But the reality is it said how long will it take 80% to decompose, and decompose means we're getting rid of it, right? So that means how long does it really take for 20% to remain is another way. So you got to kind of infer from the question. You have to read carefully and see what it's actually saying. I personally, I'll just tell you this, when I went to work this for the first time, I was tempted to put in 80 here instead of 20, but then I read, 80% to decompose, that means it's only 20% left. So you use these, you could have chosen any one of these forms of the integrated rate law for the first order reaction. I just find that I use this one a lot for these kinds of problems for first order. It's just usually, it's very handy to do that. Okay, let's work another one. This one, okay, it says the reaction of butadiene gas with itself. So in other words, two of them add together and they could produce octane. No, that's not octane. Not sure what that is. I have to think about it. Anyway, it's probably a butadiene. Yeah, this is going to be a pretty complicated one. This should have multiple double bonds in it. So it's not octane. It's some kind of a octene, but there's probably two bonds, or up to 4 bonds, I think, will be double bonds. Anyway, doesn't really matter for this. Anyway, this reaction says, here's our reaction, okay? It says the reaction is second order, so that means this is second order with respect to the butadiene. Has a rate constant of 5.76 times 10 to the minus second liters per mole per minute. Let me write another way you could write this. I'm going to just cross this out. This would be my preferred way. That's reciprocal molar. Do you see liters per mole is not moles per liter, so it's the inverse. And then inverse minutes. It's a little more straightforward in my opinion. You could write it that way though. I've seen it both ways. I'm just putting it the way I prefer. I kind of grabbed this problem from another source, and so I just thought I would. I like the problem. I just didn't like how they said the rate constant. So under this set of conditions, this is what you see, and it says if the initial concentration of butadiene is 0.2 molar, what is the concentration remaining after 10 minutes? So I will look at that. So it says second order. There's our key. Here's our second order rate constant. So we got that. All right. So we need the second order equation. So the second order equation is 1 over A sub t, where that's the concentration of A at any given time t, is equal to kT plus 1 over concentration of A sub 0. That's your initial concentration. So we know the initial concentration, but we don't know the concentration A sub t after 10 minutes. So let's solve for that. Let's put in everything. So we're trying to solve for that. That's what we don't know, but we have everything else. Okay, so let's put it in. So 1 over A sub t is equal to 5.76 times 10 to the minus second, reciprocal molar, reciprocal minute. Okay, and that's times 10 minutes. And plus 1 over our starting concentration, which is 0.200 molar. So here, these minutes will cross out because this is 1 over minutes times minutes. And then, so I'll work all this together. So let's do another round of simplification. 1 over a sub t. And then I'll do all the math here. And that is equal to 5.576. And in terms of units, all that's left here are reciprocal molar, because 1 over molar over here is the same as reciprocal molar, which is this, right? So they just add together. And then I just flip both sides to get to a sub t. So a sub t is going to be 1 over 5.576, which is 0.179 molar. So in 10 minutes, we go from 0.2 molar to 0.179 molar. Now, how can I check my answer? Well, I can go ahead and plug in this for a sub t and solve for time, and I should get 10 minutes. And I plugged that in, and I did get 10 minutes. So that's a good indication that it's correct. So you can do little things like that. If I go back up here, same deal. I can go ahead and plug in 175 seconds and see if I can get a sub t divided by a sub 0 to equal 0.2. And you can double check your answers that way. Okay, let's look at another problem. Now here's where kinetics could actually save your life. Once you reach the age of 21, you are legally able to obtain alcohol and drink it. And so I wanted to talk a little bit about the kinetics of drinking alcohol. Turns out when I was a postdoc at the University of Iowa, in Iowa City, Iowa, I studied alcohol metabolism. And so one of the things I did was I got accustomed to the kinetics of when people drink. And so I'm just going to draw something, a little sketch here. So if we look here, we got, I'll just draw a little, okay, so blood, alcohol content. That's how we do that. That kind of gives your alcohol as a percent of your blood that you have present in your body. And what I'm going to show you is just approximate, okay? So we have time. And let's say you take one drink, okay? And one drink isn't a 32-ounce glass of Mad Dog 2020. One drink is one 12-ounce beer, more or less, I mean, with the average sort of 5% alcohol content, or one 6-ounce glass of wine, or these are fluid ounce, one 1-ounce shot of 80 proof or 40% alcohol. So that would be like your scotch or rum or some of the hard liquor. That's a drink, okay? When you drink, there are two kinds of kinetics that take place. There's the kinetics of it assimilating into your body, so it goes through your stomach, and then you reach maximum blood alcohol for that drink. So your blood alcohol increases until it reaches a plateau. Typically, now things like if you're a male or female, if you have food in your stomach or not, those things can change what I'm about to tell you. This is just on an average, okay? What your weight is, stuff like that. What I'm showing you is for about a 75 kilogram person, more or less, okay? And so you'll reach blood alcohol content peak right around a half an hour. So 30 minutes, could be plus or minus 10 minutes depending on your, like I say, what those factors. But just be aware that when you take the drink, it takes about 30 minutes to hit maximum blood alcohol, and then your body gets rid of it in a zero order process. And if we look, your blood alcohol content is a concentration. It's not molarity, right? But it's a percent concentration. We've kind of talked about percent concentrations. And for most of the time, it is zero order until the very, very, very end, and it starts to curve off a little bit. But that's pretty much it. And on the average, you process about one drink per hour. And there's nothing you really can do to speed that up. It's you can't drink coffee, you can't, all that stuff will not change how fast it takes you to process alcohol. Now, there's a lot of studies where I think I watched a Mythbusters once where they found that people could perform better in certain tasks if they were like, oddly enough, I remember slapped in the face. But that doesn't change your blood alcohol content. That, if anything, just changes how well you can operate while you're drunk. But it doesn't really help get rid of the blood alcohol content. So those things just will not work. Now, so here's some implications, and you got to think about them before you drink, because while you're drinking, you're not going to care, and you're certainly not going to be thinking about kinetics. Okay, so from the time you take your first drink, okay, takes 30 minutes to reach maximum alcohol content for every drink you take. So imagine if you were at a party or gathering and you were hovering near point, let's say you were hovering near 0.06, and you decided, I'm going to have one more drink and then I'm going to hit the road. It's possible that at 0.06, first of all, you will be impaired. For the most part, the average person will be impaired. They will have impaired abilities. You pretty much, once you hit 0.03 blood alcohol content, you start to show signs. The average person will start to show signs of being impaired, and of course, at a blood alcohol content of 0.08, you are legally drunk in Idaho and most states. I was looking at this for other countries. Some countries, 0.06 is called legally drunk. Anyway, so imagine you took a drink and then you hopped in the car. You could actually start driving and not be legally drunk, but if you're still in the car 30 minutes later, that one drink could pop you up to legally drunk. So it's never a good idea to take one for the road, especially if you're close to some limits of being impaired or not. You should probably take your last drink, and if you drank a bunch, obviously you'll need to account for about 1 hour for every drink you took. But let's say you had one drink, you should probably wait an hour and a half or something like that before you hop in the car. That'll make sure the drink is pretty much cleared out of your system. So that's something to keep in mind. I think kinetics is important to think about when it comes to drinking, because too many people get pinched for drunk driving and harm other people, harm themselves, and it can really, I've seen it really screw up people's lives, getting pinched for drunk driving. So being careful in how you manage your drinking is going to be important, and there is a kinetics to it. For pretty much just count on an hour for every drink you take, and these are your drinks. Okay, so let's take a look at a realistic sort of situation. So I said alcohol clearance in the body is a zero order process. 75 kilogram person processes about one drink an hour. This, and I said you can't really speed this up. It's just the way it is. Only time will go. So let's say if so it turns out that males and females get rid of alcohol a little differently. Females are a little faster than males at getting rid of their alcohol out of their blood. So let's say that you have a blood alcohol content of zero point 0.1. Now at that point, you're drunk. 0.08 is legally drunk. You're over legally drunk. You may not be in the incapacitated or anything like that at that point. But that's a point where I think is realistic, where someone might think, oh, I can drive, I'm still okay, but you're drunk. You're actually not okay. You're not okay to drive for a lot of reasons. And so what we want to do is, I mentioned that about 0.3, if you can get to about 0.3 or below, then you should be able to manage driving, I think. The average person will not be impaired at all in that condition. So, boy, so crooked. Anyway, so let's figure out how long it will take to get rid of your blood alcohol content so that you can drive. So this is a zero order process, and for males, it's 0.015, and females on the average is 0.017. That's blood alcohol content. We're just, instead of doing molarity, I'm doing this in blood alcohol content because that's kind of the legal way of measuring it. It's hard to know, oh, you have 20 millimolar ethanol in your blood doesn't really help you when you're trying to think about this problem. So we can treat blood alcohol content just like concentration, no problem. So we'll try this calculation first in a male and then in a female, and we'll see just how much this rate constant for getting rid of your blood, your alcohol in your blood, will, how much faster it will be. So first let's do the males. So we know that A sub T is equal to A sub 0 minus KT. That's the alcohol, that's a zero order integrated rate law. So our A sub T, we want to get to 0.030, and we're starting from 0.10. I'll throw in another 0 just to keep the sig figs happy. And then minus, this is 0.015 times T. Okay, so we'll do the math. We got negative 0.700 minus 0.015 T. And I'm going to solve for T, and this will be in, I didn't put the, I just realized this. the units for this are in reciprocal hours. Reciprocal, not reciprocal. Yeah, BOC per hour is what it is. BAC, blood alcohol content per hour. We'll do it that way. Okay, that's what the units are. So, and these are BACs. So when we're done, it will be in hours. So we'll divide both sides by minus 0.015, and that will give us our time. But before I do that, I should fix my math. I just caught my ear. You were probably yelling at me through YouTube. There we go. Now I got it. Let's try it again. 4.67 hours. Wow. So it's going to take a while. That's like 5 drinks. You'd have to get rid of 5 drinks. So if you don't have 4.67 hours or where you're not drinking and you can let it go, then you better get someone to drive for you, because that's how long it will be. That's for the male. That's about 75 kilograms. Let's look at the female now. And so we'll do the same thing. This is for male. Here's female. Okay, so let's try this again. So everything is the same, except now we just have a slightly different rate law, a rate constant. So here's where we have the 0.017 BAC per hour times time. And now we do the math again, and this time I'll do the math correctly. 0.070 is equal to minus 0.1. Sorry. Okay, minus 0.017 BAC per hour times time. And then I can solve for time. So in this case, about 4.1, I guess that would be 2. And that is it's hours. That is a smaller amount of time, but it's still significant, over 4 hours. So can you imagine if you did a calculation like this to find out when you could drive safely? That would be interesting. Your friends would probably say, boy, that person sure is drunk. But anyway, I just wanted to show you this because too many people get into trouble because of alcohol. I've known so many people who have. This is the truth. I am not much of a drinker myself. I've never ever been drunk in my life, but I will drink some beer on occasion, but never more than, really I rarely drink more than 1 beer in a sitting, and no more than 2, because usually I get sick of it. And I do not like wine much at all. In fact, I don't even drink it. And I do like scotch and brandy and rum, those kinds. Sake, I like that too. And I found I do like tequila, but I only drink, like literally I'll drink maybe 2 drinks worth, so 2 fluid ounces, and I like it straight. I don't mix it with anything, and just keep it real simple. And I don't drink a ton. Anyway, I still want to just communicate this because obviously I am unusual that way, and I think I would just mention that if you are a drinker, think about how you drink, because you can keep yourself out of trouble and protect your family, protect you, protect the other people that are out on the road. A little paying mind to the kinetics that I've shared with you will make a big difference. All right, let's move on to something else. So this part is the last sort of problem I want to work on. I want us to look at how we have a first order decomposition of hydrogen oxide, uh, and it will turn into water and oxygen. You can kind of see this here. And so we're going to go ahead and do that. And the color here just symbolizes the concentration of hydrogen peroxide in real life, and they're saying it here too. It's colorless. I'm sure you've seen hydrogen peroxide. So it's just a pictorial. So from this information here, we want to figure out what is the rate constant for this sucker. And so we can see that it takes 2.16 times 10 to the fourth seconds to turn from 1 molar to 0.5 molar. And then if you add another, well, let's do it in hours. It takes 6 hours, 12 hours, another half, 18 hours, it cuts in half again. At 24 hours, it cuts in half yet again. So we can determine from this what the half-life is. And because it's a first order reaction, the half-life is the same, no matter what the concentration is. If this were zero order or second order, the half-life would be changing under each of these instances. And that's the problem with using half-lives in those other two cases. But in first order, totally can use half-life, because half-life is repeatable. So we keep cutting things in half every 6 hours. So the half-life is 6 hours. And so we know that the half-life is 6 hours, and let's do this in seconds. So we know that the T1 half is equal to 2.16 times 10 to the fourth seconds. And we know that because that's kind of repeats over and over again. Every 2.16 times 10 to the fourth seconds, it gets cut in half again and again and again. So if we know that, we also know, and this is the key here, is we know that T1 half is equal to 0.693 divided by the rate constant. So if we know T1 half, we can substitute that in there and solve for the rate constant. So I can flip-flop these. So I can also say that the rate constant is equal to 0.693 divided by the T1 half. Or I'll punch in the number for it, 693 divided by 2.16 times 10 to the fourth per second. Seconds. And when I do that math, it'll give me what the rate constant is for this decomposition reaction. So that would be 3.21 times 10 to the fifth, negative fifth, reciprocal seconds. So 3.208, and I just rounded that to 0.1 reciprocal seconds times 10 to the minus fifth reciprocal seconds. So that's a handy thing to know. So if you know the half-life, you can calculate the rate constant. If you know the rate constant, you can calculate the half-life through this relationship right here and right here. Okay, so here's a handy little summary that kind of ties everything together for zero, first, and second order reactions. And so here's the rate laws you would see for those. Here are the units for each of the that you would see. Now, I want to say something about these units. That's if you were using molar and second. it's really, these also could be, millimolar. You could use different concentrations and times. It could be minute, millimolar. All those things could come into play here. This is just when we're using molar and seconds. But the truth is, sometimes it can be per minute, it can be per hour, it can be, all those kinds of things. And so this is just kind of a generalization. It's not. You do not have to have it always in these units. You can think of it more like this way. For a zero order, you'll have a concentration divided by a time unit. For first order, it will be reciprocal time units. For second order, it will be reciprocal concentration units and reciprocal time units. For instance, these. Okay, here are the integrated rate laws. I'm not sure the way this turned out, just that those are all there that way. So concentration, I'm going to change this. I like this to A sub t, A sub t, A sub t equals those values. And remember, for first order, we have a lot of different choices. The plot needed for a linear fit, if you get a linear fit from this plot, then it's zero order. If you get a linear fit from this plot, then it's first order. If you get a linear fit from this plot, then it's second order. And by this, I mean, let me be more specific. A sub t, if you plot A sub t, I want to change these to A sub t. Okay. If you plot A sub t versus time, you get a straight line for a zero order. If you plot natural log of A sub t versus time and get a straight line, then it's first order. If you plot 1 over A sub t versus time, then you get second order plot. And k is minus the slope. Well, you can see that right here, because this is the linear form, where this part goes up here, right? Same thing here. Your slope is minus k. This is your y-intercept, which fits up there. And then here, k is the positive slope. And you can see it right from this line. Here's your y-intercept. And then, as I mentioned before, there are half-lives, and so you can calculate the half-lives for these zero order and second order. Here's what they look like, but you'll see that they always depend on the concentration. So whenever the concentration changes, the half-life does too. That makes this not very useful, but this one is very useful. The first order relationship between half-life and k is independent of the initial concentration. It's a constant itself, and that's why we use it for first order reactions. There ends the stuff on integrated rate laws.